Okay, welcome to Engineering 255. This is a second video of the chapter 7. In this video, we're going to revisit the idea of the chapter 7, and we're going to use some example to explain what you need to do for the calculation in this chapter. And the topic for this chapter is about the internal loadings. So in the first video, we introduce there's 3 internal loadings that you need to know in this chapter. And these are the internal loading that include a normal force, which is a force along the length of the member. And we also call this as actual loading. The second one is the shear force. So the shear force is the force that is tangential or parallel to the acting surfaces. So if you apply force, the force is parallel to the cross-section area, and that is what we call the shear force. And the third one is called the bending moment. So the bending moment is the moment that tends to make things bend. So with the following picture, you can see the difference of the 3 different kind of internal loading. The first one is the first one here is what we call the actual force or normal force. And the direction of that shows what is the positive direction. So if you have a normal force that going outward is positive. Okay, and that's how we define the direction. The sign convention is very important. So if it go outwards of the element, so it depends on which side you look at the element, and that direction is going to be positive direction. For the shear force, then the shear force is if you make the element to rotate clockwise. So if your shear force try to rotate a member clockwise, then this shear force is the positive. So if you look at this one here, this one going down, and it tends to make this one rotate in clockwise. And on the other side, the shear force is positive when it goes up, because that is the direction that will make this piece on the right-hand side turn clockwise. So that's how we define shear force. It's different from the tension. And the third one, the bending moment, is the bending moment tends to make the piece go upwards. And so this is a little bit different from the previous one. So both of these two are making rotate upwards. So it's not defined like a clockwise or counterclockwise as when we are calculating the moment, but this one is that when you're looking at internal loading, when the moment make the object rotate upwards, then that is how we define the positive. So that's the internal loading. Let's use some example to explain how we do the calculation. So over here, I'm going to start with an example. We wanted to make the decision, what is the normal force, what is the shear force, and the bending moment at the point of C, of this beam right here. So you look at the right-hand side, this beam is fixed at the point of A, and we want to find the midpoint, which is the point of C. The loading is a distributed loading, it's a triangle. So meaning at the beginning, the loading is larger, at the end, the loading is smaller. And start with this number here, represent 1200 Newton per meter. And when we solve these kind of problem, the first step is normally that we will find the supporting force. So if we wanted to find a supporting force, and this supporting force is the fixed point A. What are the supporting forces that we will have in the fixed point? Well, when you have a fixed point, you're going to have two forces, x and y direction. So this is going to be AY, this is going to be AX. Fixed point also have a supporting moment, and this moment is going to be counterclockwise as the positive. I'm going to put MA in clockwise direction. Now, again, the direction is arbitrary. You can always change the direction if you find out the solution to be a negative. How do we find the supporting force? Well, in this distributed load in the chapter 5, we told you you have to change the distributed load to a concentrated load and find a location of the load at a certain point, which is the central point. So we wanted to represent this one as one resultant force, and that location is what we call the centroid point. And the resultant force is just total force. So the total force through a triangle is going to be the area under the curve. So that's going to be 1/2 of the base, which is 3 meters, multiplied with the height of the triangle, and that is going to be 1200 Newton per meter. So you multiply this, then you will get 1800 Newton. So the resultant force is going to be 1800 Newton. The central point for the triangle is going to be 1/3 from the base. So 1/3 of the length at the bottom, and it's going to be equal to one. It's going to be 3 meters divided by 3, and which is going to be 1 meter. So it's 1 meter away from the point of A. Once you find this distributed load represented as a resultant load, then your problem becomes this. So the question will become, this is a simplified version that transform the left-hand side into the simpler graph. You have a resultant force here, which is 1800 Newton, and you have reaction force, supporting force, and supporting moment. And here, this is supporting moment, this is AX, this is AY. And we also know the distance between this one is 1 meter. And you just need to use the summation F, X equal to 0, and we only have one force in the X direction, which is AX. We use summation F over Y equal to 0, and that is, we have AY, and we have 1800 going down, so it's going to be minus 1800 Newton, and that gives us AY is equal to 1800 Newton. And we can do summation moment, and you have to pick a point. If we pick a point at A, and it has to be equal to 0. And at the point A, we have a moment, and that is moment of A. Now the direction matters, so let's just say this is the positive direction. This is the moment A, and we have another moment which is caused by the R, and that moment is going to be clockwise. So we're going to use minus instead of positive. The positive will be counterclockwise. The 1800 Newton force is going to make it turn this direction. So it's 1800 Newton multiply with the lever arm, which is 1 meter, and that is equal to 0. So we can find out our moment A is going to be 1800 Newton meter. And that is the direction of counterclockwise. All right, so when we want to find the bending moment, the normal force and shear force at A, we can either, and we just need to cut the member at the point of C. When you cut it, you're going to draw a smaller version of the free body diagram. And you have to remember use these convention to draw the direction of the internal loading, that is actual loading, shear loading, and also bending moment on that smaller piece. So we can have two different choices. You can draw it from the left hand side, or you can draw it on the right hand side. In this picture here, we draw the right hand side part, which means we are going to cut this member at here. After we cut it, and we want to determine just right at the point of C, what are the internal loading that is caused when we do this section method. So here we cut it. When you cut it, it's on the right hand side. So this is the actual loading that we said going out is positive. The shear force here is the force that tends to make it rotate clockwise. So it going up, because when you go up, it will tends to make it rotate in this way, which is clockwise. And the bending moment is going to be the N sub C is the moment that will make things rotate outwards. So this is the direction, make it rotate outwards. Now, how do we determine these three things? That is the question that is asked in this problem. When you do that, we end up looking at this portion of the element, and you only have a distributed load that's starting from the point C to the end of the B. You discard anything on the left-hand side, and that's nothing to do with the right-hand part. And therefore, you only have a distributed load. You're going to do the similar thing when we do the overall R at here. And that is the triangle that we draw at here. So let's calculate the total resultant force just for the section of the C to B. We're doing the same thing. You have 1/2, and you're going to have the total length right here, which is the 1.5 meter. That is this one here. And you also need to multiply with the height. Well, the height is going to be 600 Newton per meter, because it started with 1200, but it's on the very far left at the point of A, and use the similarity triangle. We are cutting this triangle in half, so the height will be in half of the 1200, so that's going to be 600. So multiply this all together, and you got 450, I think. Yeah, 450 Newton. Once you have this, we can determine the internal loading similar to the previous one at here. So let's look at the internal loading. First, we look at the summation f of x, and we only have one force at x direction, which is the N sub c, and that's equal to 0, because there's nothing else in that direction. So this is our internal actual loading, which is equal to 0. We look at the summation f of y, and we look at one force going up, which is the VC, and one force going down, that is the resultant force of the triangle, which is 450 Newton. And therefore, this has to be equal to 0. So V sub C is 415 Newton. The next thing we do is the summation moment at the C, and that is equal to M sub C. Now, this direction, I'm going to define this direction to be the same direction as we define it as a positive. So I'm going to make this one as the positive. And that's equal to M sub C. And any other force will make it rotate about the point of C. This N sub C is equal to 0, so it's not going to make it rotate about the C. This V sub C is right at the point of C, which will not make it rotate about C as well. So the only other force will make it rotate is going to be this 450 Newton force. And this is going to make it rotate as the same direction as our N sub C. So we're going to plus the 450 Newton multiplied with the lever arm, which is 0.5 meter. That is equal to 0. So M sub C is going to be negative 225 Newton meter. So here we solve the problem, and the normal force is going to be 0. The shear force is going to be 450. And the bending moment is going to be negative 225 Newton meter, which means the actual moment should be go this way. And that is the solution for this problem. Let's look at another one, just give you a different perspective of the problem. So in this case, we have a beam that is supporting at 2 points. One is point A, one is point of B. You have 3 different loading, one at 500 and 200 and 300 pounds. They acting at a different point. The location is specified at the x-axis, and we want to find the shear force bending moment at point C and point D. We can do similar thing that we did before, but let's just find the supporting force first. For the A, this is a roller, a ball, so this only have AY. A roller only support up and down. For the point B is a pin, so it has an X direction, it has a Y direction. So this is going to be BX and BY. That's the only two support that we have. So we're going to do a summation f of x equal to 0. In x direction, we only have bx, so bx is equal to 0. We do a summation force at the y direction equal to 0. In the y direction, we have ay, we have by, and we have 3 force going down, which is minus 500, minus 200, minus 300, that's equal to 0. And this will give us AY plus BY is equal to 1,000 pounds. We need one more equation. We can do a summation moment. Now, when you do summation moment, you have to pick a point. In this case, I'm going to pick point B because we have a 3 loading acting on the point B. I can save a lot of calculation without consider any force that go to the point of B. This has to be equal to 0. And let's look at what other force can cause any of the moment. So the AY is going to make it rotate clockwise. So let's make this one to be counterclockwise as a positive. Again, this direction is arbitrary. You can define any direction that you like. You just need to follow the same direction when you do the calculation. So AY is going to make it go clockwise with respect to point B. So I'm going to say minus AY and multiply with the lever on. The lever on is going to be this much, which is a 14. And then this 500 is also going to make it go clockwise, which is positive. And this will be 500 times the level on. The level on will be 8. It's going to be 4 plus 4. And then these are not going to create any of the moment. This will create a moment. This moment will be clockwise. Yeah, clockwise. So we are going to make it negative, and that's going to be 300 times the distance. The distance will be these two together. That will be 8. And you make it equal to 0 so that we can find out what is the AY. So AY is going to be equal to 2400 actually it should be 4,000 minus 2400 and divide by 14, and that should be the loading in this case. If you divide this, then you got the answer, which is 171 pounds. So that's my AY. Once you find an AY, you can find a BY, because the BY is simply equal to 1,000 minus AY, which is going to be 1,000 minus 171. You have 829 pounds. So that's our reactions, our supporting forces. Now, the next thing is that you're going to start with certain point to find out what is the reaction, the internal at the point of C. So if I want to find the point of C, and you can either use the right-hand side or use the left-hand side. I'm going to use the left-hand side, which is more easy to see how it goes. So let's just cut this member from A to C. So this is going to be the C. This is the point of A. We have a loading at here, which is 500 pounds. And this is 4 feet, and this is 6 feet. We have an AY at here, which go up. That is 171. And the internal force is going to be this one, which is make it go outwards. This is going to be N sub C. And you have a shear force. Shear force has going down because this one make it rotate clockwise. You have a moment, that's something make it go upwards. So this will be the moment of the C at this point. And then we're going to use our equilibrium equation. Let's use the summation f of x equal to 0, and only force at x direction is mc, so there's no actual force or the normal force in this case. Summation moment f of y equal to 0. We have 3 forces. One is 171 going up, 500 going down, v sub c going down, and that's equal to 0. So the v sub c is going to be equal to 500 minus 171, and that is going to be 329 pounds. Okay, now the last thing you do is summation moment at the C that is equal to 0. And we are going to use the point of C. If I use point of C, and we have to define direction, I'm going to follow the same direction as the blue color one. So I'm going to say this is going to be positive direction. So I have N sub C. And 500 pounds is going to make it rotate the same direction. So it's going to be positive 500 times the lever arm, which is 4. And then A is going to make it go to the other direction. So it's going to make it minus 171. And the distance is going to be 10. And that's equal to 0. So, and then we can multiply the 500 times 4 and minus 171 times 10, and that will give us 290, and that means the n sub c is going to be negative 290 pound feet. So then that is the solution for the first part of the point of C. Then the step 3 is that we can also find the point of B by cut at the point of B, of the D, sorry, it's D. So if we wanted to find the moment, the internal force at the D, I probably would not start from the point A because there's so many things on the left-hand side. You can use the right-hand side, which will simplify your problem. So we're going to look at, we're going to use DE components. So here is the DE component. This is where our D is. This is where our E is. We have a loading at the end of the E, which is 300 pounds. And at the D point, we're going to draw the internal loading. So this is going to be N sub D. And what will be the shear force? The shear force will go up. This will be V sub D. And the bending moment is the moment is try to make it rotate outwards. And this is the bending moment will make it all outwards. And then we find the summation F. If x equal to 0, we only have 1, which is n sub d equal to 0, summation f of y equal to 0. We have 2, which is equal to v sub d minus 300 equal to 0. So our v sub d is equal to 300 pounds. Always remember your unit at the end for the end answer. Then we find a summation moment at the D, and because D has a lot of different force, so I'm going to simplify the calculation. That equal to, now we're going to define direction, follow the blue color one. So this is clockwise will be positive. In this case, M sub D, the 300 is going to make it rotate clockwise as well. So we're going to positive 300 times the distance. So the distance is 2 feet. So we multiply it with 2. And that gives us M sub D is equal to minus 600 pound feet. So in this way, it's very easy to find the internal force at point C and point D. Okay, so this is our first part. Just kind of review the chapter 7.1 and give you some example here. I'm gonna give another example, which is the three-dimensional example. We can also solve three-dimensional problems, and this is kind of a real application that you have a sign, and we're gonna assume the sign is a uniform. Because when you assume this one is a uniform, you can, to simplify the weight of the sign by putting the weight to be at the center of this plate. The mass of the plate is 650 kilogram. The support is a fixed support, which is the end of this point. And here, this is the fixed support. We want to find the internal loading at point A. Okay, and you also get the information like maximum uniform wind loading on the sign is 900 Pascal. So what is Pascal? Pascal is a pressure. Pascal meaning 900 Newton per meter square. Like every meter square, you have 900 pounds of the wing will hit on this side. And what is the direction that you're going to hit on this side? It's going to be the direction they go into this board or this screen. So that is the direction that you actually going to apply the load. So this problem become a three-dimension. If we draw this in a three-dimensional way, you will see how we visualize it. So this is the drawing of the actual situation. We're going to have an X direction, Y direction, a Z direction. And this wing at here is going to be the wing that perpendicular to the plate, which is going to be in the X direction. How much of the force? You have to calculate that. So pressure is equal to force divided by the area. And we need the force. So our force is going to be equal to pressure times the area. And the pressure is equal to 900 Pascal. And area is this area, which is equal to this area. And that's 6 times 2.5 meters squared. Okay, so 6 times 2.5 is going to be equal to 15. And we multiply this, and that's equal to 13.5 thousand Newton. The 650 here represent the mass. You don't use 650 as the force because mass is not a force. You have to multiply with a g. So when you use 650, this over here, this number is coming from 650 times 9.8, and that is equal to 6.376 thousand Newton. The direction of this is going down, which is in the z direction, the negative z direction. At this point of A, we are going to have three direction of the force. You're going to have a force in the x direction. You have a force in the y direction. You have a force in the z direction. You're also going to have a moment in the A direction, a moment in the y direction, a moment in the z direction as well. So you have three moments. Three direction of force, three direction of moment. And how do we calculate this? Well, you simply just use the same way we do the summation of F equal to 0, summation moment equal to 0. So if we do the summation F equal to 0, I'm using a vector. We're not looking at the individual direction now. And when you do this one, we have like two forces, right? For this whole part here, just look at this one here. The force is going to be two components. The external force, you have a wing load, which is negative 13.5 thousand, and that is in the I direction, that's the X direction. You have the weight, which is in the Z direction, is also minus 6.376 thousand, is in the K direction, negative K. You also have F of A, which is going to be AXI plus AYJ plus AZK. And you will see there's no J direction, so this one equal to 0. AX is going to be equal to 13.5 thousand, and AZ is going to be equal to 6.376,000. So now we find out the two internal force. These two force, if you look at the bar, so if this is the column, you have x direction, which is the direction in this direction when you cut the section, and you have a k direction. The k direction is going to be in this direction. So this one is our normal force. This one is actually our shear force. So you have a normal force going down, actually is going outwards, that's positive. The shear force is the force that tends to make it rotate. So we're looking at the top one, it will tend to make it rotate which direction? It's kind of like a make it clockwise direction. So the V is going to be a positive number as well. And this one is going to be 13.5 thousand. This is this one here. Now, how do we find a moment? So if you want to find a moment, we have to pick a point. Let's say the moment at point of A. And we choose this point because I don't need to worry about the f of A, create any of the moment. We only have the moment of the A. This moment is going to be a vector because it composed of MAX, MAY, and MAZ. And this is not the only thing will cause the moment at point A. The other moment is created by two forces in the system, which are these two. This one and this one will create a moment. We are going to use R cross F, where your R is going to be the R from A to G. So we're going to have R A to G cross your F. Your F is going to be this one here. Okay, so let's look at what is the RAG equal to. RAG is equal to point G coordinate minus point A coordinate. Let's make A as the origin. So the G point is going to be in the same direction of the X. So you're going to put 0. And in the Y direction is going to be equal to 3. In the Z direction is going to be 5.25. And your force is going to be minus 13.5 thousand, 0 for the J, minus 6,376,000. And you do a cross. When you do a cross, how do you do a cross? You put I, J, and K. Second row is going to be the R, 0, 3, 5.25. The last one is going to be minus 13.5 thousand, 0, minus 6.376 thousand. And you find the determinant. This one plus MA is equal to 0, which means MA is going to be equal to minus of this. And once you do this, you will find the solution. So this is the end of our first part. I'm going to do another video to talk about the rest of the things that you need to know.